In the winter, that's his
Yep.
snow activity.
All right. Okay, I got it up and running. Finally. Okay, guys. So let's just get into the first problem here. The first problem will hopefully demonstrate the idea. So right now, if you want to take the derivative of this, we have a method. And I asked you to take this derivative 2a. So first, let's do it. I mean, we haven't learned the product rule, whatever that is yet, so we're just going to do it without the product rule. So doing it without, and this is what I'd recommend. Anytime you can avoid the product rule, you probably should, because if you can avoid it, then that means it can be done more easily. For this one, yeah, if you just expand this, so let's multiply it out. You got x squared times 4x is 4x cubed. You got 3x squared. Notice it's still y, not y prime. And then you got negative 8x. And then you got negative 6. And so the derivative would be 12x squared plus 6x minus 8. Pretty easy, right? No questions are helpful. So the product rule, I'll show it to you. I think I'll just show you the rule, and then a couple days from now we'll go over kind of some deeper logic behind it. So I don't want to get bogged down in like proving that it's true or anything to start. So the product rule is this. It's really simple. The derivative of, let's say I have two functions. So let's say I've got something like, I like to write f times g, but then sometimes people get confused because then we start talking about functions named f and g. So I think instead I'm going to use a and b. A times b. So imagine a and b are two functions. So a could be, for example, a could be x squared minus 2, and b could be 4x plus 3. Fair enough? Mm-hmm. So the derivative of a times b would be a prime times b plus b prime times a. That's it. That's called the product rule. Okay, so let's do it. Let's take the derivative of this with the product rule. Like we said, we're going to let A be this first thing, and B be that second thing. Am I safe to assume that it's fairly obvious that this is a product of two things, right? It's thing times a thing. So, okay, so then let's do the derivative. So the derivative would be A, so what's A prime? Some people like to list them out, by the way. This is a pretty common thing. Maybe you start doing this and then later on you realize you actually don't need to see it. But this is a pretty standard approach where you actually list out, that's my A, that's my B. So that would be my A prime, that would be my B prime. And so according to the product rule, the derivative ought to be, well, it better be that or else we made a big mistake. A prime times B, what's B? It's 3 plus B prime, which is 4, times A, which is x squared minus 2. So that's one way to write the derivative. Now we could just, to double check, is that really the same as that? Yeah, if I expanded this out, I'd have 8x squared plus 6x plus 4x squared minus 8, which of course is the same as that. So as you can see, in the case of two little, this last step, usually we're not going to worry about that. Usually this ends there. For this one problem, let's show yes that woo, sigh of relief, it works. It's yeah. I was worried it wasn't going to work. It did work. So if you look at the next couple, now first of all, so the motivation for this might not be clear because you might go, well, okay, what's the point of learning this new technique if this was even easier? Well, hopefully B, C, and D will convince you. B, C, and D are going to be much easier with the product rule because expanding those out would be a huge pain. But also, there's a whole bunch of functions out there. We haven't gotten to this yet, but you can imagine, like pretty soon we're going to start talking about derivatives of functions like 4 to the x power and sine of x. And really the only way to take the derivative of a function like 4 to the x times sine of x would be to use a product rule and treat it as a product of functions. There'd be no other possible way. So that'll be something second semester when we start throwing in trig and whatnot. Okay. All right, let's do one more together, and then I'll skip B. B's, I mean, you can see B would be a pain to expand. It wouldn't be like the worst thing, but it's going to be much easier to do B. Oh, by the way, yeah, Bailey, this is yours. There was no like label. I wasn't sure what it was. So if you want to get that after class and tell me what it was, I can get it entered. Okay. Look at C. Ugh, gross. You've got x minus 1 plus root x times squeak, squeak, squeak. That's nice and squeaky.
That little bracelet. Did you hear that? No. Is it going to the bracelet every single time?
All right. So this is the A. This is the B. Could I have called this the A and this the B? Yeah. Sure. Right? Multiplication is commutative, meaning you can swap them, so it doesn't matter. So my A prime is going to be, let's take the derivative of this thing just separately. 1 minus 0 plus 1/2. 1/2 x to the negative 1/2, aka 1/2 root x. So that's A prime. And then B prime would be 50x to the 9 minus 6x plus 7. Now, here's the best part. That's actually really good because you don't have to simplify this out into a single like standard form. So you go A prime times B. Luckily, you got the whole width of the page here, so try to get it all in one line. So this reads A prime times B plus B prime times A. And A was disgusting.
Beautiful.
That's it though.
Yay.
That's the derivative.
Wow, super simple. Could easily drop that. I don't even know where to begin.
We get the end behavior because the dominant term would be, well, first the domain is only from 0 to infinity. It's just because of that one term. And the dominant behavior would be x to the 11th. So all we know is that it goes to infinity. I mean, it might even be boring. It might just do something like this. But I imagine there might be some, I don't know. Who knows? It could do. There's definitely a bunch of other terms. Also, when x is 0, the whole thing is 0 because of this term. So you know it has the origin, you know it's end behavior. But other than that, you can't get much information.
That is a beautiful girl, that left one.
Mm-hmm. Thank you. I appreciate it, Jesse. Okay, so why don't you guys, well, hell on. Maybe to keep the video concise here, I'll just, so once we're done covering this stuff, you'll be able to knock out the other two on your own. Quotient rule. So this is kind of front loaded here. I'm going to show you the 3 rules, and then we can take some class time to do them. Shouldn't take too long. Quotient rule is also pretty simple. It's just a formula. The quotient rule says the chain rule is going to be the most confusing of the 3. Always is. So the quotient rule, number 2, Now let's say you had A over B, a quotient, right? The derivative there is going to be A prime times B minus B prime times A all over B squared. That is not a second derivative. That is a squared, second power. Okay, so I want to clarify that. My B looked up and stuff. Okay, so A prime times B minus B prime times A all over B squared. By the way, I mean, it's just for the sake of like being thorough, if you Google this, you might see it written like this, where it's an f of x and a g of x, in which case it's the same thing. It just I think it looks more cluttered this way. So you'll see it written something like that. So f prime times g minus g prime times f all over g squared. I prefer this to single letters. Okay, so 2a. Let's differentiate this two different ways. So let's do it the without first. Again, without is much easier in this particular case. But in the case of B, question B is impossible to do any other way. There's no other way to really do it. Maybe some really clever algebra trick, but anyway, so A, so since we have x squared over minus 4 over x, both terms get divided by x, right? So you first rewrite this as x squared divided by x, 4 divided by x, which of course 4 over x I can write as that if that helps me, right? You can write it as 4 over x if you want, but just keep in mind that 4 over x is the same as 4x to the negative first, and so the derivative would be 1. What's next? 1 plus 4x to the negative 2. Let's actually simplify this. You'd have 1 plus 4 over x squared. If you wanted to get fancy, you could, not like this is fancy, I shouldn't say. Anyway, you could write this 1 as x squared over x squared, and add the fractions, and have x squared plus 4. Everyone understand that step there? If I thought of the 1 as x squared over x squared, common denominators at the tops. So anyway, these are both two equivalent ways of writing the derivative. Well, I guess all three are equivalent, right? Let's do it with the quotient rule. All right, let's identify who's A. Now this one you gotta be careful. Does it matter who we call A and who we call B? Yeah, it's because of this minus, well, because of the minus sign and because one of them is just getting squared at the bottom. So that's a huge difference. So of course, this is the top. So this guy is going to be our A. A is going to be x squared minus 4. B is going to be just x. So A prime is 2x and B prime is 1. Okay, so let's take the derivative. Quotient rule says A prime times B minus B prime times A. Be very careful. It's very easy to mess these up. Very easy to like drop a negative or something. You guys see that? See what I'm talking about? A prime times B minus B prime times A all over B squared. Now in this case, B is just a single term, so squaring it's pretty easy. Bear in mind if B is like a binomial or something, then you have to, the whole thing gets squared. So often you'll see brackets. This. Okay, so we got, let's see, I got 2x squared minus 1x squared, banana theorem and all. It's a single x squared. And I got minus negative 4, which is a positive 4. Once again, big sigh of relief. It worked. Amazing. Why don't you guys try B real quick? take a minute, and then I'll quickly go over the solution to make sure there's no confusion. And then, is everyone? Yes.
So, you want us to simplify these in the end, right?
No. Well, okay, it's yeah. Yeah, thank you. That's a good question. So simplifying is like, by example, I guess I can answer that question. So remember on question 1B, how simplifying that would have been disgusting. And it wasn't going to make it look any nicer anyway. But in this one, we all agree that this is a lot better looking than this, and it didn't require a ton of work. So I'd say, what my answer to that question is, if you can easily simplify it into a much nicer looking form, then do it. But don't spend a whole bunch of algebra. You guys, as you learn this more and more, you'll get an intuition for like when it's a waste of time to simplify and when it actually does make your expression a lot nicer. So on question 2B, you're gonna, you'll have a very short, easy simplification at the end of that, I think. But keep the bottom as just 3x squared plus 5 squared. Anyway, get it started. I'll go over the answer and then I'll, touch on that. So hopefully you had that at the minimum, just kind of identified top's the A, bottom's the B, there's your A prime and your B prime. So your derivative would be A prime times B it's kind of weird how sometimes you say something, I don't know, brain stuff, and you write it. So A prime times B minus B prime times A, all divided by B squared. Okay, and then I ask the question, can I very easily write this in a nicer way? In this particular case, yeah, because I've got 3x squared minus 6x squared, which is negative 3x squared. And so I'm sure we'd all agree that this is easier to read than this. So yes, we. If any of you guys are taking the AP exam, you can leave it like this.
You what?
You can leave it like this on the AP exam. You don't have to simplify.
Do you recommend leaving it like that?
Probably, yeah. But I mean, this class is also supposed to be like college prep. So if you would, I think in any university class, you might lose some credit, or you got to be able to go from here to here.
Okay.
But yeah, so if you guys are taking the AP exam, yeah, you can leave it. And generally, it's recommended to do that because every step you make is there's some probability of you making a mistake. Okay, does everyone understand that? Are we okay? You sure?
Yep.
No questions? Interesting kind of structure. I don't know. 5 minus 5 plus.
Yeah.
Okay, chain rule. Okay. All right. I'm going to give you the technical definition here. 95% chances this will confuse you. So don't feel bad if you're. The example will make a lot of sense. I promise. So the chain rule says that. So we've talked about a function times a function, and we've talked about a function divided by a function. So what do we have left? You could do, if you had function times a function times a function, you'd have to do the product rule 2 times. You'd first do, so if you had A times B times C, you have to first go like product rule on this, boil it down, and then do it again. Or do the B and C first, associativity and all. But we haven't done a function of a function. So if we go, what's the derivative? I'm gonna use F's and G's this time because with A's and B's it looks really weird. What if I had F of G of X? Gross, sorry. So a function inside a function. Well, here's where the first one actually makes a lot of sense. If I said the derivative of F with respect to G times the derivative of G with respect to X. Now this is kind of hand wavy, but that's some cancely bobancely. That's always nice. So what that suggests, it's not rigorous, but it's close to rigorous. To actually prove it, you always come back to the limit definition, etc. But anyway, so you have, I'd say they're more for like an analysis class. So you might take that in college, possibly if you're like math majors. But anyway, so the derivative of F with respect to G, that's F prime of G of X. And this is G prime of X. And what did we figure out? Well, we figured out the derivative of this function with respect to X. So, okay, confused?
Mm-hmm.
Yeah, okay, good. So, I'll write it a different way. So same idea, I'll write it a different way. What if I want to talk about, you do have to know this form though. I mean, there's a lot of questions where the way it's phrased, this is the easiest way to solve the problem. So they're on this problem set, so you can get some practice doing them. But like, if you want to look forward, look at like problem, 20. Where you have a table of values, and the only way to really solve that problem is by thinking about it abstractly in this way. Well, I should say that's the only way to do it, but that's pretty much. Okay, so here's a different way. I'm gonna go in reverse order of complexity. So this is the rigorous definition. What if I think of it like F of U? Okay, F of U. So they love the letter U in calculus. They're always using U's for some reason. U substitution, etc. So anyway, F of U, the derivative of that would be F prime of U, and then you tack on U prime. Does that look a little bit simpler, maybe? Like you could maybe work with that a little bit better? Mm-hmm. This last one, you'll really like this last one. This example is great. Okay. Let's suppose I had something like 7x to the 4th plus 9, and it was raised to the 10th power. What would I do? Well, wait a second. Couldn't I think of this as being u to the 10th power? Yeah, I'm going to call that my u. And watch what I'll do. Watch how simple this is. The derivative of this would be 10u to the 9th, and I tack on a u prime. There's that u prime.
Oh.
Okay. So I take the derivative as if it was just a simple function. This right here would be my d in this analogy or this definition here. This would be like my df over dg, and this would be my dg over dx. But look how simple it is. You see, all I got to do is if I pretend like this is banana to the 10th, my derivative is just 10 banana to the 9th, and I just tack on a little u prime. Now, in this context here, so I'd have 10 u to the 9th. And what would I tack on here, do you think?
For 28x.
There you go. That would be the derivative, which of course I could simplify this into 280x cubed times 7x to the 4th plus 9.
Very good.
That's not too scary, right?
That's much easier.
Much easier, much easier. Okay, so let's,
What?
oh, sorry, Jamie.
No, whatever.
What we're gonna do that. So the example from our problem set is differentiate this dude two different ways. So we're gonna see the chain rule in action. Okay, we'll leave that up there. And jot that down, by the way. That's we're gonna come back to that later. So, and I strongly encourage you to see if you can understand this. This would take some fairly deep thought. It's not going to probably come to you right away, but how what we're doing on this is the same as this. It really is the same. Okay, so 3a, our function is this, right? So our method right now, let's do it without. What's the without method? You gotta expand it, right? You gotta be like, so you go, oh, 2 is nice. You can square that. If that was a 20, you'd go, I know that's horrible. Okay, but 2 is easy, right? So we're gonna have 4x to the 6th plus, what's the next term?
Next to the
20x cubed. The last term is 25. Cool beans? Hopefully.
Yes.
So the derivative is going to be, again, it's just the function being rewritten. We squared it. So 24x to the 5th plus 60x squared plus 9. Okay, that was easy. Let's do it with. Okay, so to do it with, all you got to do is you say, well, I'm going to think of this as being y equals u squared. Okay? So the derivative would be, here's the chain rule in action. By the way, what's happening here is we're going dy over du, treating u like a variable, and then multiplying it by du over dx. What that gets us is the derivative of the function with respect to x. Okay, so this first term here, what's dy over du? It would just be 2u. Everyone understand that? So what's the derivative of x squared? 2x. What's the derivative of u squared? 2u. If you're taking with respect to u. And then you tack on u prime. So let's look what happens. 2u times u prime. So what's u? 2x cubed plus 5, yep. And then what's u prime? 6x squared. So there's u prime. So this reads 2u times u prime. And of course, if I multiplied this out, I would get that. Let's do one more together. Maybe we'll do 2 or 3. Maybe we'll do this whole page together, because this is usually, you guys would agree with, right? This is the most confusing one. Okay, so look at B. So I'm erasing here. Think of B. think of b as u to the 10th, right? What's the derivative of u to the 10th? 10 u to the 9th. And then you just got to tack on a u prime and you're good to go. All right. Tack it on. Well, multiply it on. Okay. So in practice, it's actually pretty easy. The really hard part, I think, is to really grasp what you're doing is tough. And I wouldn't expect that to come right away. So the first thing is again, I haven't not taken any derivatives yet. I'm just in my mind lumping this into a single symbol called u. And then I say, well, the chain rule says that the derivative of this would be 10 u to the 9th. And I just got to multiply that by u prime. So I have 10 u to the 9th multiplied by, notice the parentheses, u prime, which is 8x minus 1. Cool beans?
Yeah.
That's it. The next one.
Okay.
Notice, guys, I mean, obviously these are all just saying take the derivative, but pay some attention to the notation. These are all notations that you should be familiar with. So like on C, we define a function and ask for df over dx. On B, we defined a function and asked for f prime of x. And on D, we just put the derivative operator and said take the derivative of this expression. They're all equivalent, of course. Okay, the next one. Who is u?
3x minus x to the 5th.
Yep. This is an interesting function, I think, because yeah. That's a weird domain. Okay, so this guy inside here is the u. So by the way, the function inside the function, the little function, the inside function, is this. And the outside function is just the square root function. That's all okay, so the derivative would be, first I'm going to say, I'm thinking of this as, the square root of u. So what's the derivative of the square root of u?
Over 2 root 2? No. 2 root u? I was right.
Understand that? Cool with that? So just to remind you, so remember what we're doing. This first term is the derivative of the function with respect to u. And then the thing we multiply that by is the derivative of u with respect to x. And when you multiply them, you get that spice of life. Cancel Bobancy. Okay. So this is the derivative of this, pretending that u is just the variable that we're dealing with. We said, but actually, we're not. That's not our variable, really. X is our variable. U is actually a function of that. And then, okay, derivative of u, well, u prime. So when we finally write our answer, I guess I got to erase this now. It would be 1 over 2 root u times, don't forget the parentheses. What's the u prime? 3 minus 5x to the 4. Now, you pretty much always see this get written.
Isn't that any different than writing 1/2 times u to the negative 1/2 times u prime?
1/2 times u. No, that's correct.
Okay, I just want
Sorry,
that's
actually,
what I did. I was like, oh, it's wrong.
I didn't mean to say it was wrong if I said that. Sorry. No, yeah, this is the same. This would be equivalent to writing 1/2 times u to the negative 1/2 times u prime. Now, if this is multiple choice, for example, or you just want to make your answer pretty, would be pretty standard to write it. If you can get it all into one expression, that's nice, one fraction. So that's going to be your standard way of writing that answer, because of course, this times the fraction, you get to multiply by 1. Okay. How are we doing for time? Should we do one more? You guys can get D, right? Okay, so then look at the way this practice is structured, just to clarify, is problem 4 is 4 product rule problems. So you know in advance, just do the product rule on all 4. Just practice it, make sure you do it correctly. 5 asks you to do 6 quotient rule problems. Did I say that wrong? 5 asks you to do 6 quotient rule problems. Number 6 asks you to do 8 chain rule problems. Notice some of them, like if you look at 6F or 6D, you might go, shouldn't I use the quotient rule? No, force yourself. Make it a chain rule problem. Okay, you can. The first step on these chain rules is like, just a quick example. Like on 6F, when you have 1 over 3x plus 2, like that. Yeah, write this as 3x plus 2 to the negative 1, and now do it like a chain rule. See what I'm talking about?
Yeah.
If you're really ambitious, you can prove the quotient rule using the chain rule if you want. Basically, it's this kind of idea. It's writing one of the terms as a negative power and using the product rule. You don't have to do that. And then from then on, 7, so like 7, 8, 9, all those are just some. The part of the problem is figuring out which one should I use. So like on 7a, that's probably going to be chain rule, and then a lot of them use the chain rule, but you might have to use the product rule or the quotient rule or whatever. So, okay, that's all I got for you today. Sorry, I talked. Tomorrow we have a fire drill tomorrow. So.